Instead of trying to figure out which specific neuron is firing, what if we just took that time series information, fed that to a model, and gave it labels of what a person was actually thinking and feeling? That's like new and previously was not possible. We don't want to delude ourselves. We want to have the data speak for itself on what's possible, what's not, where we're like, okay, yeah, it seems to make sense. The numbers are lining up, the results are coming out. If this was true, the possibilities are endless. Like what if we had real ML researchers, computational neuroscientists, and software engineers look at this problem and like bring this field forward like 20 years? The stuff I tell you now is the results of our work from like 6 months ago. So take all of the timelines that you have and like compress them a bit more. And so like it's coming soon. And there's a question of like, how does that look? And that basically is like full human-computer interaction.
So when I first visited this place, it seems like a very unassuming place for a startup working on reading the human mind and reading thoughts. This is a problem that impacts every human on Earth, and it's all starting in this apartment. I guess we could start with talking about why now is a special time to study reconstructing thoughts and mind reconstruction.
Yeah, now is a very special time. I think we're kind of seeing this reflected everywhere, but the development of AI, in particular, on novel deep learning methods and new architectures, mean that we can kind of do some things that were considered impossible for, and now it's kind of more of an engineering problem. The one that we're looking at here is the advent of like large transformers, large pre-trained models, learning like a good representation of the world, generative models that can work from like limited data to fill in the blanks. And so in this field of neuro, something pretty interesting is happening where we're now able to approach it from a top-down perspective, where we look at noisy readings from time series, and instead of trying to figure out which specific neuron is firing or what functional group that's a part of, and using a neurophysiological approach to understand, oh, this is because of motor cortex, and this is like, your hippocampus, etc. And then inferring from that, what if we just took that time series information and fed that to a model and gave it labels of what a person was actually thinking and feeling? So now you have this approach that's top down. You're not trying to understand the biology. You're not trying to model every neuron firing. You're just going to go straight from the data of what you're recording on the scalp or however you work with neural data to the ideas. So that's like new and previously was not possible.
How do you decide to work on this problem? It's such an ambitious problem to want to read thoughts. It seems like an almost impossible problem to work on. And you guys, I think, are having amazing results in decoding images from thoughts. So what led you to work on this, I guess?
Yeah, great question. I think you think mind reading and you're like, this is probably one of those very pie in the sky problems, intractable. And sort of, I was feeling that too. And so my background was in sort of ML research. So I was doing some, computer vision stuff at Sustain Lab. This was at Stanford under Stefano Erman. And so, you work in applied ML enough and you kind of start to see patterns. You're like, oh, okay, like these models can actually be better than humans at some specific tasks. So, try to find some pixel variants in millions of images. Right? This is where models are very good at probabilistic modeling. This is where you're very good at picking on the nuances of just, values in data. And that's what humans are not the best at. And so you take that, principle of what these models are good at, and then you look at areas that haven't historically had that approach, this deep approach. Neural data has been one of those. So this was like maybe 3 years ago. My friend and I, we were talking like, why don't we do this on, brain data? So turns out there was actually a paper that came out called MindVis, and that was kind of like a pretty breakthrough piece of work that basically showed the light for me. And then, you saw, hey, here is evidence that you can go from, this non-invasive imaging to decoding an image of what the person was presented. And this is like a semantic transfer task. And you see that and you're like, oh, okay, like this is proof that this method could actually work. So obviously we're still like kind of unsure. So I went and worked at the lab. And I was like, oh, okay, saw for myself how it worked and it actually worked, and you can improve the architecture as well. And then, we answered more of that question at MedArc at Stability AI. And, we keep doing these like experiments for ourselves. We don't want to delude ourselves. We want to have the data speak for itself on what's possible, what's not, what are the trends. And so only after we did a bunch of, modeling and sanity checks and reproduction, where we're like, okay, yeah, it seems to make sense. The numbers are lining up. The results are coming out, the hypothesis seems to have more weight. And so especially from like the academia perspective, you want to be extremely, cautious about jumping to conclusions. And so we want to let the data speak for itself. And so that's kind of why it took a bit, but we were, if this was true, the possibilities are endless. And so we kind of put a lot of effort to answering that questions for ourselves, to convince ourselves.
True in the sense of non-invasive being a fruitful path to follow.
Yeah, the truth in the sense that you can use deep learning to model non-invasive time series data to uncover semantic ideas of consciousness. So now it's like, is this an engineering problem or is this like a completely impossible thing? And so you see, oh wow, look, we've done this on images. You can take the same idea to other aspects of consciousness.
What year was that? What year was it where this was thought to be impossible? And then I think MindViz, I don't know what year that came out. When did the door open where it was like, okay, this is a good path to follow? Maybe like past 5 years or?
I think this field has been kind of looking at this a few times actually. So for example, when AlexNet came out, that was like a pretty seminal architecture where you're now able to have like a CNN architecture that can do a bunch of image recognition tasks. And then there's like the advent of GANs, and fMRI is also pretty new. And so people have been really seriously trying to understand, can we decode vision, what you're seeing from fMRI for the past 10 years? And you start with very blurry images and you're like, maybe it's not doing and then you get into,
And that was around 2015-ish?
Yeah, 2015, 2018. Okay. There's like the advent of like CNNs, and then there's GANs, and then there's more like hierarchical models, and then sort of like transformers coming out, and then diffusion coming out, and these methods get better. And so the core contribution of MindViz was they did a vision transformer to encode the data from the fMRI side, and then they did a diffusion model to go from that to generating the image. So the benefit of a diffusion model is you can give it a high-level vague guidance on, I guess, the summary of what someone's thinking or feeling. So the idea of a fire truck. And then the diffusion model can fill in the blanks and make a pretty high-resolution image. Whereas before you wouldn't be able to do that. So I guess people have always been looking at this field, especially since fMRI came out. It was like, can we uncover conscious activity from this data? And we just simply didn't have the tools before. And so we start with very simple like linear classifiers, and then we go into vague black and white, and then we go into more shapes from GANs that still kind of morphed up, and then you go from there to like more high fidelity stuff.
For context, fMRI is like those giant machines where you like roll someone into it or something, and then it's like, just for context of the size and cost, I guess.
Yeah, it's this giant magnet, and it's usually supercooled by helium. It's all around you, and MRI is magnetic resonance imaging. So they're basically changing the parameters of the magnetic field, and different parts of your body react differently to the change in the magnetic field. And so fMRI is functional MRI, and it's measuring more real time. And so what fMRI is measuring is this thing called the BOLD response. So blood oxygen level dependent response. Essentially, there's oxygenated and deoxygenated hemoglobin in your brain. And when neurons fire, they consume glucose and oxygen, and then you get different concentrations of the hemoglobin flowing around. The oxygenated and deoxygenated hemoglobin have different magnetic properties. And so fMRI is mapping that. And so maybe it takes about 5 to 10 seconds to measure that BOLD response because you got the blood flowing in response to neural activity. So not measuring directly neural activity. It's kind of like you have a city and then you're measuring the passage of people by measuring like the pollution, the CO2 coming out. And so that's what fMRI measures. Machines are 3 Tesla up to like 7 Tesla. So it's like very strong magnetic fields, like 60,000 times what the Earth provides.
I want to touch on the two main segments of this problem, which is reading what's going on in people's minds and then decoding those thoughts. So maybe we can start out with what even are brainwaves when we're thinking what is even happening. Like I think people obviously know we have neurons, but what is actually going on that's decodable to like what the data you're sampling. What even is a thought? Not on the philosophical level, but on like the physical level. And like what are you looking for when you're putting these things on people's heads?
Cool. All right, let's start with the brain. That's kind of how we view the world, where we get emotions, where we get ideas, all that. And your brain is made of a bunch of neurons, around 86 billion of them. A neuron is a cell, and it composes, and it's interconnected to other neurons. And so if enough other neurons give it a signal, then it's gonna start an action potential. So that's basically, it's sending electrical impulse down the long side of the neuron, the axon, and then it's going to release some chemicals. We call them neurotransmitters, and that will basically give signals to other cells. And neural activity is sort of the basis of like cognition. So we got, based on different stimuli, so different experiences, different thoughts, you're going to have different groups of neurons and parts of the brain be active. And so the whole idea here is, how do you measure that? And so on the outside of your brain, you're going to have some non-invasive measurement like EEG, and we're going to have electrodes on the surface of the scalp, and you're going to be measuring some slight change in voltage, because individual neurons will be creating a voltage differential, and groups of them, some will be slightly more positively charged, some will be slightly less positively charged. So you're going to measure that in real time.
And so you can sense these outside of the skull.
It's very, very weak signals.
Right.
So like 10 to 100 microvolts. So it's very, very weak, and that's why it's like a pretty sensitive instrument. But you can measure on all of your electrodes, some are more positive, some negative, and you see that propagation in space and time. And what we call brain waves is just the frequency of oscillation of your brain activity. You know, lower waves, frequencies, or maybe when you're resting and sleeping, and higher frequencies are, you know, when you're having like an insight or like active cognitive tasks. That's what we talk about in terms of brain waves. But really, the whole point is to get a better understanding of what's going on inside. So you can measure that with a variety of instruments, either measuring the voltage directly, or measuring the magnetic field created by it, or indirectly through the blood oxygen that we mentioned earlier. And so there's a bunch of ways of trying to understand what's going on. And you get this time series information of just the raw activity, and then you go from that information to the decoding side, which is like, okay, how do we go from this reading to understanding the semantics? What is this person actually thinking? What are they actually feeling? What are they experiencing? So these are like the two halves that you mentioned earlier.
So I kind of want to go through the different ways you can read the signals in the brain. There's invasive methods where you actually enter the skull. There's non-invasive where you guys actually have like the EEG cap that reads signals from the surface of the skull. Maybe you could show the cap you have and maybe go through the different methods of reading those signals and like the trade-offs. And
yeah, sure. I can bring up some model that we just got. It might be good for illustrative purposes. So there's two main sort of things here going on. This is an EEG cap that we put on a model.
And this would go on someone's head.
Yeah. So this is like the large. And there's, you know, electrode positions at, you know, standard locations. So this is a 1020 layout. And
how many is that?
This one is 64. So if you see each location has, you know, a label like FCZ, like frontal, AF, anterior frontal, and things like that.
Right.
And then we have the electrode harness. So this is a 32 channel harness that we plug into an amp.
And so you mentioned the signals are very weak. They go into an amplifier.
Yes, they're around 10 to 100 microvolts, and that's very weak. Each one of these is an active electrode, and you put them right in the slot. And this is the reference ground electrode. So you want to measure voltage relative to something, right? So this is the reference ground electrode. This is EEG, so electroencephalography. It's measuring voltage on the scalp, and so it's non-invasive. There's a few other non-invasive measurement techniques. MEG, magnetoencephalography, that's measuring the magnetic field emitted by your neurons when they fire. And then there's obviously MRI, magnetic resonance imaging, and that's, you know, a much bigger magnet. fMRI as well. So MRI is measuring more structural things, and fMRI is measuring the functional stuff. So structural is like your gray matter, white matter, your skull, and then fMRI is measuring like the blood oxygenation. And then there's also some other modalities like ultrasound coming out or near infrared. And so those are all sort of the main non-invasive ways of measuring. So non-invasive is like you're not piercing the scalp. And then on the invasive side, there's like quite a few others like ECOG, like Utah arrays. There's also, I think, like stereo EEG as well. And so those involve something entering your brain, cutting open the scalp through the bone, inserting electrodes right where the neurons are. And so it's like very invasive. There may be some complications even without its stuff in your brain. If you can get the same thing done non-invasively, then it's a no-brainer. The benefit of invasive is you get really high quality signal because you're right where the neurons are. The voltage potentials are 100 times more strong. And then the downside is you gotta have something in your brain. So these are all the main ways you can read signal going out from the brain. And the question now is like, how do we interpret it? How do we understand what does this time series brain data correspond to in terms of cognitive activities? And so that's the whole idea of neural decoding. The task is, given this reading, how do we understand the meaning that's going on behind it? So that's sort of the whole focus of our company. So we mainly do deep learning based approaches to do that. This is like lab grade hardware, right? So this is just stuff you can buy off the shelf. Very expensive, but it works. And the whole idea here is that, things like EEG is like mature for over 80 years. You're simply measuring voltage on the scalp. And so there's like other modalities, also like varying levels of maturity. But what we really think is the most you can unlock is the deep learning applied onto such data to unlock more information. So EEG has historically had a pretty bad rep, and it made sense. You get this uninterpretable time series data, and then you're trying to figure out what's going on. And so, historical methods are like manual inspection. So this is like ERP analysis. You're like, oh, these electrodes at the back of the head spike at 100 milliseconds. And we see that happens when there's a visual stimuli. Or some others happen at 300 milliseconds. We call it the N300 component. This happens when you're confused. There's that type of analysis. There's frequency analysis where you're taking this time series, you're passing it through like a FFT, and now you get your gamma, beta, alpha waves. And you're like, oh, maybe like this wave corresponds to when you're more focused, that one is when you're more anxious. And then there's like topo map analysis. So you take the time series and you plot it in 3D space. And that was considered like the hot new thing of from 20 years ago. And just seeing like different areas. And you're like, oh, okay, this area is visual cortex, and this area is like, temporal cortex or whatever. And so our understanding and interpretation of it is very limited by the spatial resolution and the noise. There's like a lot of noise. So the whole idea here is, what if you have deep learning look at that? What if you could pick up on nuances that you can't manually do just through inspection? And that's kind of what we prove with image reconstructions. Like, oh, you can actually figure out if someone's seeing like a fire truck or ice cream cone, but we don't know what components that actually corresponds to. So that's sort of demonstrating, at least proving that you can decode semantic information from EEG. There's like a question of, how do you best decode? So that's the whole sort of crux of the problem. How do you make sure you map to a interpretable space that represents all aspects of your consciousness? So like, what are you feeling? What are you thinking? What are you experiencing? What are your intents?
And you think it's all possible via non-invasive EEG?
I think there's like a limit for sure, but it's a lot higher than what we are currently doing, much, much higher. So for example, just last year, people would be saying, oh, you can't decode images on EEG. That's only an fMRI thing, right? And so we've done it to show, okay, like the same methods apply. In fact, there's actually more potential to do so because our ability to interpret time series is a lot worse than spatial mappings. If you see sort of the size of the models and how naive the processing techniques are and how small the data sets are, you'll be very surprised to see these results. And so the whole thinking is, okay, like what if we had real ML researchers and computational neuroscientists and software engineers look at this problem, apply all of these techniques we've used in all these other areas, and like bring this field forward like 20 years, right? And so that's sort of the reason why we're very excited. It's because like the stuff we're showing is like the lower bound of what you can do. And so there's for sure a limit, right? There, in terms of information theory, there's like an inherent limit based on like your sampling rate, the noise of the amplifier, all this other stuff. But our ability to interpret that, I think, is like very, very low. We can greatly improve that. And that's why we stick with EEG, because EEG is like decently affordable, portable, reproducible. The limiting factor is our ability to interpret it, and you can apply that to other modalities later too. That's sort of like the main thinking there. Neural data has a lot of potential because it's the closest you can get to human cognition, and it's like the raw data, right? So like for example, with text, you're getting only a figment of what you decide to write down. Whatever is like online is whatever you decide to post. Same thing with images, video, etc. They're not the raw representation of like reasoning, right? You are reasoning and then you're thinking and feeling, and then you act upon that by interacting and making media and content. If we have access to that, that's like orders of magnitude more data, orders of magnitude higher quality data because you're covering the reasoning behind that.
Right.
And that's like pretty much untapped. And mainly because it's been a big pain to get this data, which is why you want to make something useful and have it sort of be part of the workflow. But yeah, you have to sit a person down and set everything up, and it's very annoying. And that's like a big reason why it isn't everywhere. But it's like a pretty untapped thing.
Maybe we could talk about what are the most interesting things you've discovered looking at this brain data. I think you said this was like a 32 channel like time series, all this raw data. What is the most interesting thing you've seen looking at it?
For images, yeah, it's really cool. We find that the decoding is much better on landscapes and food and animals rather than arbitrary objects. And there might be like a biological reason for that. Like perhaps like our brains will respond strongly more to like food and objects that are more natural. This is like purely speculative because there's a lot of confounds, and maybe like there might be more coverage of like animals than a grenade and things like that. So that's something to keep in mind, but it is still information to take into account. Another one is like we saw that the number of electrodes don't matter so much as the quality of the data coming in. So that means, are you getting good contact? So like, what's your impedance? Are you, getting that below 5 kilo ohms? What's the quality of your amplifier? Are you injecting noise? Are you having sort of line noise? Are you having interference coming from the electrodes and the cabling? Is there movement, artifacts? So all of this, basically we found that when you use like consumer grade hardware, you're gonna need like 10 times the amount of data that you would to get the same decoding performance as just lab grade hardware if you set it right. The amplifier is what matters, and these electrodes also matters, and these caps also matter. So the difference between this and like a consumer setup, and this is like the best consumer setup that maybe like you can get in a reasonable amount of money is like the emotive, and that still requires gel, and that still is much worse than lab grade hardware. And then if you go to dry and all these even cheaper modalities, it's like really, really garbage.
Right. And one of these, I think it was 2,500 for the amp and headgear.
The emotive Epoch Flex should be around 2.2K. And so that's like a very small amp, and they got their electrodes included, 32. And lab grade hardware is very expensive. The Brain Vision for 32 channels is about 40,000.
40,000, okay.
Which should not cost that much at all. The actual components to get something comparable should probably be like $600, $700.
Right. So it would be completely impractical to like read thousands of people's mind data because
it would be impractical to set up many Brain Vision stations.
Right.
And there's like, internally we're also exploring other sort of alternatives. But yeah, we can, get almost the same decoding performance on 17 channels in the acceptable lobe compared to all 64 for image reconstruction. So the main thing that matters is you want coverage on the areas that matter for the task at hand. And that's really interesting for like designing future interfaces. Some other things that we found that were pretty interesting, different people respond strongly to different things. And everyone has like a completely unique brain chemistry, physiology, in the sense that, the main things are the same. Just like how like our body, we have two hands and they're like in the right place. But the nuances are different, like your fingerprint, the features of your face. So same thing in your brain, you got different functional groups in the right area, and things generally fire in the right order. But when you're talking about nuances of ideas like decoding, how you're feeling or what you're thinking exactly, that's when there's like nuance. And so that's why you have to do fine tuning. And that's the whole idea of, can we customize this decoding method for your brain?
Maybe let's do a high level on how your current approach works for decoding images. So you have this EEG device that sits on the scalp.
Yeah, image reconstruction. The task is we will present to you specific images. We're gonna read your scalp voltage with EEG. Now the model's objective is to, given this image, given the EEG data, reconstruct what we think the person was seeing. So that's image reconstruction task. So the model only is given the time series EEG, and then its goal is to predict what the person sees. So the setup is a few stages. So the first one is data collection. So you have the person sit down, you have the cap put on, you make sure all the electrodes are set up in the right location, the impedances are low, you make sure they're comfortable, you make sure the distance to the monitor's fixed, you already predefine which images are gonna show exactly when. It's all like set up, it's like quiet, it's dark, it's not too hot, not too cold, and then you start the experiment. You collect that data and then you pre-process it. So you like basically match the specific EEG to the specific like image that you see, and you make specific windows. So let's say 1 second epochs. Now you create this data set, generally normalized, clean data of the time series data and the corresponding image stimulus. So in this case, let's say you're sampling at 250 hertz, you have 32 channels, and you get 32 by 250 NumPy array, and then you're gonna have the data for the label as this image. Now the modeling is basically the last step, where you are given this data set, and the model's objective is to go from the EEG to predicting the right image. So you want to make sure...
And you know what the image is.
You do know what the image, so this is supervised ML. So you're basically saying, given X, predict Y, and I'll tell you how far or close you are to the label by having like a loss function of predicted Y and actual Y. And so you want to make sure that there's no like cheating going on. So you're gonna have a training set and a test set. So in training set, we're gonna have unique image categories, and we're gonna have to make sure on the test set, there's no overlap. And so this is kind of where you make sure, oh, like not only is like the image category not there specifically, but you wanna account for some leakage. So for example, there might be a bunch of like dogs and cats and hyenas, whatever, right? You wanna make sure that on the test set, at least you're aware of the fact that, oh, there's a bunch of four-legged animals here. Maybe the model is just gonna predict generic four-legged animals and get close enough. So there's like, that, or like the image properties like color, pixel density, pixel color, distribution of shapes, brightness, all of these features, these are confounds that you wanna think about. So yeah, you have your training set and you have your test set. You train your model to basically do very well in the training set, and you evaluate on the test set. And so that's kind of what we're doing. We want to be very careful and intentional about measuring this in this setup, because you want to be sure that the model is understanding the meaning behind the EEG, rather than just saying, oh, this EEG, I don't know what it means, I'm just gonna throw it in this bucket. And so like if you're doing a classification task of like, I don't know, a bunch of different objects, and there's like 10 fixed objects, perhaps the model's not actually understanding, oh, this EEG corresponds to when they're like seeing a fruit. And instead it's, all the data has a specific characteristic, and we're just gonna throw it in that bucket called fruit. And so we wanna make sure we're doing the semantic decoding objective, learning that latent representation instead of a naive classifier objective. And that's sort of like the stuff that has changed, is thanks to deep learning, we can do this new stuff on modeling to a latent space.
And so the main problem is generalizing and not overfitting to the data that the model's been shown.
Both, right? So if you're overfitting, that means you're doing really well on the training set and you're doing very bad on the test set, and that's not useful. So you don't want to overfit. And then generalization, there's like a couple dimensions. So the first one is, can we generalize from these categories to novel categories? Can we generalize from other people to a new person? Can we generalize from decoding like scene images to internally imagined images, or even mood, or other things that are different tasks? Can you generalize across hardware? There's like a whole suite of questions on generalization. So we're working on mainly two things, which is capabilities, how well can you decode, and the second one is generalization. How well does it work in a real environment? And sometimes generalization might not matter that much, in the sense that, say you have a pretty decent coverage of stimuli, then maybe you don't need to generalize to novel stimuli. Let's say we like basically show all the animals and all the food and almost all the objects. Maybe that's sufficient. Or maybe you cover like a large enough group of people that you don't need to worry about generalizing to a novel participant. These are like theoretical questions that we don't really know the answer to, and that we're trying to find the answer to through our research too.
Why is this such an important problem to solve? Why would we want to read the brain? It's something we don't really think about, because it's kind of like the seat of our consciousness. It's kind of like when you're in water, you don't really think that you're like surrounded by water.
Yeah.
So why do you think this is such an important problem to be working on? And like, what are the downstream implications of being able to read the mind?
Yeah, well, our entire existence is based on like our consciousness, right? You are aware and you see and feel things, and it's all predicated on your ability to experience. All of our ideas, all our conceptions of who we are, all of our experiences are all happening in our brain. You get particles and you get waves coming at you, and there's no inherent thing as color. There's just like a specific frequency, and then you interpret it a certain way. It's like the basis of our whole existence, and it's pretty crazy. And we don't think about it too much, because otherwise we'd probably go insane, right? So I guess, why is it important to deal with consciousness? I think that there's a lot of challenges we have in day-to-day life that stem from an inability to communicate effectively. So, I'm speaking to you and I'm basically writing to your mind. Don't think of a white elephant, right? So like, I am using speech to transmit an idea across, and it's very challenging to get exactly what I want to tell you. What is the context of why I'm saying this? What's going on in my mind? What's my background? And we get all sorts of conflicts and misunderstandings from that. Or were you trying to communicate to computers? You're like struggling to like design a thing. You're trying to open an application and you communicate by pressing buttons on your keyboard and mouse. We also struggle to talk to AI. So this is like a pretty interesting direction we're seeing where you're like prompting and reprompting ChatGPT, or you're saying Midjourney, no, I want to generate this specific image. It's very hard basically for other people, computers, and AI to understand exactly what you want, and that's a communication problem. And so I guess what excites me the most about neural decoding in the field of BCI is it's allowing for read, not just regular communication. So what that means is without you having to say anything or do anything, in theory with good neural decoding, I can know what you're thinking and feeling and doing just from reading. So that's not an inherently bad thing, just like automation is not an inherently bad thing. This is technology that lets us do something new, something that hasn't been possible before. And that's just leverage. It lets you do things more effectively with fewer resources. And that can either be used for good or for bad, right? So good is basically all of these areas where how can I get my thoughts across? So we're talking to a therapist. What if they could know exactly how you feel in 5 seconds? Or what if you can have a game that reacts to how you're feeling so it's more enjoyable? What if you could diagnose your mental conditions like instantly or in 15 minutes instead of 8 months, which is what it takes for diagnosing autism for children? What if you could understand, just get this point across in work or interpersonal relationships? What if you could have software that does things that you wanted, but you weren't aware you wanted it? What if it did it instantly, right? So there's all this good stuff and there's all this bad stuff, which is, what if other people read my mind? What if I don't my thoughts are not contained in my head? What if people use that information to make my life terrible for some reason?
And I just want to clarify, that's not possible with EEG. It's only broad, patterns within brain regions, I think, or?
Yeah, like EEG has inherent limitations. We're never going to be able to figure out why a specific neuron fired and exactly when. You're capturing stuff that diffuses through the scalp and the skull. And so you're going to be picking up on a high level summary of semantic information. So what's your mood? What's on your top of your mind? What sort of the idea of the image you're seeing? And so that's like an inherently different technology than something like Neuralink.
So it's almost like the skull is like this privacy layer, almost.
Somewhat. I guess it's basically it's like a low pass filter. You're gonna have high frequency information that will just be averaged out, and then you're gonna get the low frequency drifts that you pick up. In a sense, yes, you do have privacy on the high frequency information. Specifically, like an example is like, let's say I'm writing an essay. It might be very terrible at figuring out exactly which key I press and what I intend to write there, but it's gonna be pretty good at understanding, oh, I'm trying to write about this science fiction story about a rocket ship and there's like a cowboy on it. Maybe you can pick up on the ideas. So that's sort of interesting. I don't think you can pick up on like your credit card number or things like that, right?
Just broad themes.
Yeah, that's sort of the idea. That works really well with EEG. Like,
do you think you'll ever get to the point of pinpointing exact? Because I know Meta did a study where they could decode text. I think this was like February.
Oh yes, they had their control labs on, I think, EMG on the wrist.
Right.
And so they were trying to pick up individual actions there.
That went through the motor system.
Yeah.
So that wasn't direct brain waves.
No, I don't think so.
Got it.
Yeah. So I guess what I'll say is the downstream implication is full understanding. So now, we're not even very aware of ourselves, right? Like what are the top 5 emotions you're feeling right now? Exactly what ratio, why, and how did you feel like 5 seconds ago, 10 seconds ago? Like, it's just very hard to be living a conscious experience and also be super hyper aware. And
so it's more than other people, it's also just you understanding.
Yeah, you could get a summary of how you're dealing with the thinking. You could get in theory, it'd be really good to understand how we're thinking so that we can be healthier and happier and more effective. And all of this is just communicating to ourselves and to others. And so I guess how this affects the world is it allows for interfaces that read how you're thinking instead of having to express it. This allows for like pretty proactive, affective interfaces. And so what that means is instead of you having to do something to trigger an experience, now it just does it before you have to do something. And so you can have pretty interesting feedback loops. We can guide how you're thinking towards like a more healthy, productive state. There's, things that act proactively. Like anytime you open your computer or if you're trying to do something, right? What if you could it does the thing without you having to, right? So that's like a new form of interface that we have not unlocked yet. So there's an improvement in both bandwidth as well as expressivity in communication. And I think that's really important because we're moving more and more towards a future where software is more and more automated, more and more powerful, and then our ability to interface it is going to be the bottleneck. That's why we see, companies like Cursor get very popular because now it's expanding that bottleneck where normally you'd have to like copy paste code and you'd have this.
The main bottleneck is just intention, like expressing your intention.
Yeah, expressing intention, giving context, and I think that trend is going to continue. And
the ultimate kind of way to express intention is to get to the root of it, which is
yeah, and so especially when we're talking about development of like large, powerful AIs. How do we make sure that they understand what we want and do what we want? How do we make sure that they can empathize and also share these human values? Like that's where communication is like a very big factor. And we're kind of seeing that you can be much better at communication than we currently assume is possible with EEG and all these other modalities.
right.
And so I think the difference between like these utopian use cases and more dystopian use cases is the focus on preserving human dignity. So that's the whole idea of how do you make sure that the privacy and control is owned by the individual rather than someone who does not share their values.
So you think this would have to all be local? Like this couldn't go to a server?
Maybe you could encrypt it, maybe you could map it to a shared space where you can't like go backwards. There just has to be like a focus on human well-being at the end of the day. So this technology is going to be made no matter what, right? Just like how AI is going to be made no matter what. It's just too many actors and then competition and incentives. You cannot prevent people from doing it. Sure, you can have regulation in one country. What about another country? What about Cayman Islands or China, right? And so I think the best way to move this towards like a more productive, healthy direction is to be really good at the technology, and then you set precedent for human well-being and privacy and safety. I think we see that being done by companies like Anthropic, and they kind of push the whole field towards focusing on human well-being through AI safety. That's kind of a big reason why we're working on this. Not only is it cool and interesting and exciting and technically like very fun, it's also, I guess, where we get a lot of our meaning and mission is moving this direction to a field where it's just generally better for people, right? So it's not all doom and gloom and it's not all like sparkles. It's just leverage technology and you want to see where can you move it better and how can it help people. So that's how I view this technology. And I think like a lot of people have a more knee-jerk reaction to neural decoding, like 1984, Orwell, and all these other things. And I think it would be really productive in the discourse to not just talk about all the bad things that could happen, but also the good things that could happen. It's just not inherently bad to be able to get your thoughts out of your head. Yeah.
So how close do you think we are to being able to decode images? I know you guys are working on images, emotions, video right now. How many years is it until a normal person can just walk into a pharmacy and just buy, something that can read their mind and be able to just use it?
Probably sooner than you think.
How soon do you think?
For full neural decoding, that's like a tall order. Probably maybe in 10 years. But for very useful neural decoding, maybe 5 years or even 2 years or even 1 year.
How would you define useful?
Useful is you have a task and you want to decode something at some level of accuracy across some number of difficulties, and you have a tolerance for error, and you can do that above whatever your dimensions of analysis are. So there's like a few ways of doing that. So there's like the first one, let's just look at EEG. The first one is image reconstruction. And the question we're trying to answer is, can we take these methods that we've done on fMRI and adapt them to EEG? The question there is, how accurately can you decode an image in the test set? And this is looking at both high-level features, like are you showing fire truck, and low-level features, like is the top right corner red? And so there's a bunch of different metrics to do that. You can argue that it's like somewhat solved pretty well. So for example, on our website, you can see some of the stuff that we've done. That's done on a 64-channel EEG with like 1 second epochs on the test set. And you're seeing the decoding of novel images. So those are the best results. And there's also the worst results, which are incomprehensible images. So in terms of like human rated accuracy, like we can maybe do like maybe 78, 80% between like our image and like some randomly generated image. And so you can keep pushing that metric up. But in the sense of like, could this feasibly work? And did the scaling laws apply? 100% yes. So we've kind of already modeled that. The scaling laws is like, as a function of data set size, how well does the decoding performance improve? We basically figured out, yeah, this is not just a scaling problem, but in terms of can it work with more data? The answer is like 100%. Images do work. And then we're moving on now to evoked state. A lot of these are questions that we don't have the answer to, but we have some priors or some intuition about where they should go. And so our priors lead us to running this company because we think they'd be solvable in different ways. But in terms of like exact performance numbers, we have to do the data collection and the experiments ourselves to know. And that's kind of all we've been doing. And so that's the stuff I tell you now is the results of our work from like 6 months ago. With emotion decoding, it's evolving the question to answer, what are you feeling rather than just what are you experiencing? So on the modeling side, it could be a lot easier because you can have fewer dimensions to map out this space. Instead of maybe what we did with images, it was 1024 dimensionally in space.
And you would know what the final image is.
Yeah, you would know the ground truth, exactly. And here you're not really sure. So you must count on self-report, and you must count on like some assumptions on the stimuli you present to elicit a state.
What is an emotion? Like, what does that look like from your brain scans? Like, does that look any different from an image or?
Your images are very clearly your visual cortex. Emotion is mostly in like the amygdala and then your prefrontal cortex and then your hippocampus. It's also more nuanced because it takes longer time and there's like combinations of emotion. And so it's harder in terms of the experiment design because there's more confounds. But that's like the next question. Can we now understand how someone's feeling internally? You start from very few dimensions and then you add to that, and then you explore like combinations of emotions, nuanced emotions, for subtle emotions. You ideally increase the complexity until eventually you're going to like full thought decoding of what's going on in your mind, the topic of conversation and discussion, intents and all that. And so there's this sort of spectrum in terms of capability that is also correlated with how hard it is. And so for like emotion decoding, video decoding, image decoding, audio, that's stuff that, we could see very strong progress in like a year or two. We're like, okay, it's not perfect, but we have it basically there. But yeah, like decoding inner evoked emotions where there's sort of combinations of things or nuanced biases, adding on to full sentence decoding, full inner monologue, that stuff is probably on the order of like 5 years. And then there's a question of going from, can it work with like very expensive lab grade hardware in the basement or in a lab to portable dry electrode EEG that's affordable and works when you're moving and outside. And that's kind of what expands the timeline to like maybe 10 years. The main thing is the hardware itself doesn't change, and all that we're doing is the data collection, the modeling, and the experiment design. And that's the stuff that lets us move a lot faster than we think is the people think is possible. And so I would just say, take your assumptions about how fast things are going to move and just like cut it down into like maybe the 2, 5, 10 year range. And that's kind of what's very exciting.
And then this is kind of a high level kind of metaphysical question is, I don't know if your research has made you informed you more on how consciousness works, but we don't have to go into like the what is consciousness discussion because philosophers have discussed that to depth for hundreds of years or thousands. But I imagine the image prediction results you've had are so impressive. It makes me think that consciousness could be simulated at some point. Like if we're able to, figure out how images are decoded, will we reach a point where we can just simulate consciousness?
Yeah, simulating consciousness is a nuanced sort of topic. Like if you're talking about simulating a whole brain and, having all these billions of neurons and you're modeling the physics and, all these nuanced emergent properties, that's like a very, very hard problem that we don't know if it's possible. And then there's like another type of simulated consciousness, kind of like LLMs. You have this black box that just parrots out words, and it's like, oh, maybe that's like reasoning or something, or signs of it. And for us, like, we're kind of going to the approach of, given this time series brain data, we're uncovering sort of the ideas that's going on behind it. And so it's like a mapping problem. In the sense of simulating consciousness, perhaps you get this large data set of mental train of thought, and you use that to build a black box model that probabilistically is very similar to how the idea is. So perhaps not simulating the mechanics of consciousness, but the output in terms of what it's thinking about could be interesting. There's obviously nuances in the modeling of the input and the output, and the nuances on the individual. And so, yeah, that's like a sort of very open sort of field. But obviously knowing how people are really thinking and feeling is going to help a lot to that.
So maybe we could talk about the state-of-the-art research you guys are working on. Like you published Mind I2, which we'll talk about, and then Alljoined 1.6 million. Maybe we could talk about the data set side as well as I think it was like a 40x speed up on pre-training.
Alljoined 1.6M is a recent work that we made where we collected 4 hours on 20 participants, and each participant seeing about like 80,000 images. And that's just like a very large scale data set collection effort. It's basically twice the size of the previous largest EEG image data set. So we're already like releasing that to the public, to the science community. And that's done on consumer grade hardware. And what we basically observe are these scaling laws that depend very heavily on the quality of the amplifier. So that's like one thing. We just collect a lot of data in-house. We don't emphasize on strictly the highest amount of data you can push through the system, because we've seen that if you just throw a bunch of people at a paradigm and you haven't figured out the paradigm, or you have issues in the hardware and all this other stuff, like you're not going to get much value out of that. And so the approach is to have a very well-designed, focused objective where it's not just the sheer number of people you throw into a room with like a naive model and naive experiment, but well sort of designed one where there's a specific question you're answering, and there's like a sufficient amount of data to answer that, and you answer that as quickly as possible. And then you go on to like answering the next questions. That's the data set. 1.6M is across the whole data set, 1.6 million trials. And then Mind I2 was like some work that was like way earlier, before Alljoined. And so me and Reese, we worked on it with Paul and Tanishq. And the contribution of that paper is basically showing that you can use fMRI data of other participants to first pre-train a model such that it can fine-tune on a new person with way less data. So instead of needing 40 hours, you only need 1 hour. And that's basically showing the potential of multi-subject data to make fine-tuning faster. And we did the same thing on EEG as well. So we used a multi-subject architecture, and then on pre-training on 9 people, on the new person it would only take 15 minutes instead of 6 hours. So that's like a 96% improvement.
And the pre-training, I think we discussed that the pre-training step is essential for customizing to each person's brainwaves.
That's fine-tuning.
Oh, fine-tuning, I see.
Yes, the fine-tuning is essential, at least right now, because everyone has a different brain geometry and neural activity for even the same things.
So maybe we could talk about how decoding thoughts will change the interface to AI systems, because right now it's mostly us talking to chats. In the past year, we've seen agentic systems. How will being able to read people's minds change how we talk to AI?
I think that the way we currently work with AI is kind of convoluted, where we have an intention about doing something, and then we distill that into words, text, keyboard, mouse, and then that is then encoded into like a language model and latent space. And then that is understood by the model downstream to do whatever. It's like very lossy each step of the process. And as we mentioned before, it's also very hard to understand exactly what you want yourselves. And so can we go from just the brain activity directly to a latent space that's native to AI? Now you basically unlock an objective way for computers to understand exactly what you are intending to do or what you're experiencing. And that basically is like full human-computer interaction. And that's very powerful. So now you don't have to have this translation problem anymore. The cool thing about AI and neuro is that unlike other areas where you can apply AI in different ways and it's doing something more automated or fast or new, and those areas do better, neuro is an example where improvements in areas in neuro will actually improve the capability of AI. So this is if you have good decoding architectures and algorithms and you're unlocking human reasoning and mood and all this other stuff. Now that provides a really good data set to further improve the capability and alignment of these foundational AI models. So that's like something that Ilya Sutskever mentioned a lot. It's like, train AGI, just get like a transcript of your thoughts. And that's like super good for alignment. Your thoughts are the highest resolution, closest to ground truth information of human reasoning. And if we have that as a data set for models, now we can have models that are more human and are more empathetic and share similar values. And that's like very important for not just, capabilities, but also safety. It's like very intertwined. Yeah.
How far do you think we are from that being a reality?
Not far at all, in the sense that we're already seeing neural data help with the capabilities of foundation models. So for example, in October of last year, 2024, Musa and some other researchers from Max Planck took a speech-to-text model, removed the last layer, and then had the logits mapped to fMRI activations of a person hearing audio. And by doing that, the model, they basically fine-tuned it for that, and then they had like the heads attached again, and then it was like fine-tuned for specific model, like downstream tasks, and then it would do better than before. So it does better than the foundational models. And that's basically like, I think in terms of multimodal modeling, a pretty strong sign that just another representation of this idea is going to help a model learn better inherently, even if you're not able to decode thoughts. So we can do that already, and then you're uncovering all the semantic information that can use as well. And so this is just like another representation of data and ideas that we don't happen to, and it's already been shown to like help with the performance of foundation models.
Could we ever be in a 1984 scenario where the government has access to our thoughts, or some third party, and abuses it, misuses it? Could that ever happen, you think? Or do you think it's inevitable to happen?
I think it's possible to happen, but it's not inevitable to happen. And that's kind of where it matters. I think it's inevitable that this technology will be more capable over time, regardless of if we work on it or not. Now the question is, if by working on it, can we get this technology to a better outcome? That's kind of what we care about. Like, I want to be able to sleep well at night, right? I'm working on this because it's cool. I'm working on it because I think it could help people. And I do not want it to be used in these sort of situations. And so that's kind of when you're looking at how do you preserve that human dignity and the privacy and autonomy. So you want to prepare for it, sort of situations like that. Perhaps you encode the information on the hardware side, or you detect lack of consent and someone saying stop, or you map it to a shared space that you can't go back from. Maybe you encrypt everything before you upload it. Maybe you don't upload it at all. You can't prevent the development of this technology. Like, other people will be working on it. There's competition. There's other countries, right? And so the idea is like, given that it's going to happen, how do we make sure it happens in the best way possible?